Hi, my name is Tomáš Hrubý, and in this presentation I'm going to talk about the eBPF data plane of the Calico project, how to understand it and how to troubleshoot it. As you probably know, Calico is a CNI plugin for Kubernetes, but not only for Kubernetes. It's responsible for networking, and it provides a network policy model. That model is richer than the Kubernetes policy model. However, completely implements the Kubernetes one as well. Calico is pretty much a control plane that gathers information from the environment, compiles it together with the user-provided policies, and programs the data plane, and the data plane executes the rules. Calico can work with multiple data planes. Traditionally, it works with IP tables. IP tables are provided by the Linux kernel, and Calico only programs the IP table rules. The data plane I'm going to talk about here today is called eBPF. It's based on the eBPF technology, which is provided by the kernel. However, the code that the kernel executes is provided by the Calico project. Therefore, the eBPF data plane kind of became part of the Calico project itself. The Calico also supports other data planes, like the VPP that was contributed by Cisco, which executes in user space. And Calico also can run on Windows, and to the surprise, it can also use eBPF there. So what the eBPF brings? Primarily, it brings better scalability of services. It brings lower latency within the host. It comes with an integrated kube proxy. And that means that there's no third party that would conflict on a single resource with Calico, but the kube proxy like entity is integrated with the Calico itself. The great thing about eBPF is that it allows us to implement new features. For instance, we can preserve the client IPs when client access services over node ports. It also allows us to implement what is called DSR, the direct server return, which reduces the latency of services. And in general, eBPF gives us flexibility. It allows us to tweak existing Kubernetes features, and it allows us to implement new features that our users might want. But let me take a step back and look at the IP tables. Why do we want to replace them? IP tables do not scale very well. Every packet goes through IP tables, and the way the rules are being programmed into the IP tables is not very scalable when you have a lot of services. On the other hand, IP tables is really well understood. It's been around for 20 plus years. And over those years, it was quite battle-hardened. Also, a user can dump all the rules in IP tables, and those rules are sort of human-readable. So the services that Calico or kube proxy programs and the policies are sort of in a plain sight. You dump the rules and you can see what is programmed and what IP tables are supposed to execute. The rest of Linux takes care of routing, protocols, other corner cases, and pretty much does all the heavy lifting. With eBPF, this changes. Linux provides the environment, but the code that executes is provided by Calico. or other frameworks. There are multiple places where that code is being executed. In eBPF, we provide small programs that attach to hooks in various places of the Linux kernel. Those places are typically different than where the IP tables hooks are. We primarily use what is called TC hooks that attach to queuing disciplines on the devices. So you have a hook which is on ingress and egress of a device that sees packet right before or right after it enters or leaves the machine. The IP tables are largely bypassed, and the reason for that is that the programs can redirect packets from one device to another device. While doing so, the programs may or may not console the host routing. So the flow of the packets through the system changes quite dramatically. The downside of eBPF is that it's somewhat understood. eBPF has been around for quite a few years and is part of Calico for 3 or so years. The problem is that there are still not so many people out there who have been exposed to the eBPF technology. And unlike IP tables, it's definitely not human readable. The code is written in C, is programmed, is compiled into bytecode, and that bytecode is loaded into the kernel. So all you can get out is maybe disassembled code, and good luck reading that. Another problem, as I mentioned before, is that the node's network stack is largely bypassed. So things happen without you actually seeing packets where you would expect them to go through. Also, the Kubernetes queue proxy is useless because that proxy programs the IP tables, but if the packet is bypassing IP tables, it's not going to go through those rules. Therefore, the queue proxy has to be integrated with eBPF, and all the service translation has to be provided by the data plane itself. Another problem is the policies. The policies are code, and it's bytecode and it's assembly when you want to dump it, and it may refer to eBPF maps that have a different format and depends on the project, and that's not quite easy to decipher. So from the user's perspective, we got something which is real fast. It has great features, but it's hard to verify whether the policies that you specified through the Calico interfaces are the policies which are programmed. Contract of the host is not really used anymore because it's largely bypassed. And that may be very confusing because there are some connections that you clearly see that are connected, but you can't see it in the contract. It's also very hard to verify whether the services were programmed the way you expect, because those rules are not in the IP tables, but those rules are somewhere in eBPF maps. And there are also a bunch of third-party rules that were taking advantage of IP tables and contract and those utilities. And those legacy setups may be broken. But before I dive into how open the black box of the eBPF platform, let me take you through one more feature. In IP tables, the services were always resolved within IP tables. So when a pod was trying to connect to a service, the device of the pod would see pod-to-service traffic. And the backend would see a pod-to-pod traffic. And every packet on those connections would have to be translated. That is no more true with eBPF. We call the feature connect time load balancing. It's implemented by attaching a small eBPF program to a C group, which attaches it to every connect system call of your application. And those services may be resolved right at the connect time. So all you see on the network is pod-to-pod traffic. And there are no service IPs on the wire for traffic which is intra-cluster. It comes with no overhead per packet because we don't have to translate every packet because of NAT. But if you look at TCP DOM, it may get confusing that you don't see the service IPs anywhere as you were used to. So how does this work? A pod or application in a pod makes connect call. Connect decides it should go to a certain backend pod of a service. So all the packets that leave the application and leave the pod are pod-to-pod. There are some setups that don't like it, particularly sidecards with Linkerd that need the service IP to make decisions. And in general, this is great for TCP, but sometimes not so much for UDP. If we have connected UDP, and yes, you can make a connect on UDP, which decides the destination of your packet, the selection of the backend is done once. For unconnected UDP, with every send message, we would have to make a decision. But not to spray the packets all over the cluster, we maintain some per client affinity. But what happens if a backend dies? Essentially, the app can't tell because it's sending UDP traffic somewhere. There's no connection being maintained. And so it keeps sending it to the backend that doesn't exist anymore. And it cannot pick a new one. So we can turn this feature off. That was always possible. But since the upcoming 3.25 release, we will be able to turn it off without breaking host network applications. And we can turn it off only for UDP because the primary use case here is DNS. So when a DNS pod moves somewhere else, we need to reflect that. And applications like Nginx would not restart or would not detect that there are no responses. So this is fixed now. TCP doesn't suffer from this problem and can keep taking advantage of the speedup. I'm talking here about that feature primarily to show that with eBPF, things get faster, but they also get more complicated and not less intuitive. So let me dive now into how we can inspect the eBPF data plane. There is a utility called Calico BPF, but it's easier to access that utility straight through the Calico nodes, as this command line shows. This utility has been part of Calico since its inception and provides several useful commands to inspect the state. And in the rest of the talk, I'm going to walk you through some of the commands and how to use them. The first and probably most important is to check how the net and services are programmed. Because if you don't get connection through service, you probably want to check whether that is correct. In Calico eBPF, it consists of two maps. That's a map that lists all the front ends, and there's a map that lists all the back ends. And the front ends point to the back ends in the second map. If you use the Calico BPF with the not_dump command, you will get a list of lines that starts with a service IP that shows you a protocol. It shows you how many backends there are and how many are local. And it continues with a list of indented lines that show what backend it is and where the backend is. You can also have two services that point to the same set of backends. The reason for that is that a single service in Kubernetes can have multiple IPs, like cluster IP, node port IP, external IP, so on and so forth. The next thing to look at is the routes, and whether the routing is the same as what's your understanding. Calico uses a routing table of its own, which is not necessarily the same as the host routing. This is more of a table that maintains the understanding of Calico and what is where in the cluster. So when you dump the routing table, on the left-hand side, you will see a CIDR, and on the right-hand side, you will see an explanation of what the CIDR is. It will tell you whether it is remote or local, whether it is a workload or a host, whether it is being tunneled, if it's a local workload, to what interface it is attached. So if your understanding of the routing doesn't match what you get from the data plane, that's probably a problem. I've mentioned before that contract is a problematic point when you switch to eBPF. The host contract is no more used, but we need contract to maintain translations of the services. Therefore, eBPF implements its own contract, and that is the most important contract in the system. If there is no connection in this contract, it doesn't exist. We use a single entry that maintains connection properties, and we use a second entry if the connection is going through a service. The kernel's contract is mostly irrelevant, but there are some exceptions which I will touch on later on. So if you use the Calico BPF utility to dump the contract, you will get lines like this one. This is for the simple case that the connection doesn't go through contract. That connection would have a single entry only. First, there's the contract key, which is the 5-tuple that identifies the connection. That's the client, source port, source IP, the server's destination IP, and the port and the protocol. It also signals that this is a simple entry, that's a type 0, but most importantly, it maintains a whole bunch of information about the connection. For instance, here you can see there's a TCP connection and has been gracefully opened. SYN and SYNACs were seen from both sides, but it has been also gracefully closed. You can also see how long ago the connection was active and how long ago, how old the connection is. That's important for cleaning up those tables. In case of NAT and case of service, things are slightly more complicated. There will be an entry that shows the client and the service. That's the pre-DNet tuple. And that also contains the reverse key, which identifies the connection in the opposite direction from the destination towards the original pod or towards the original client. This tuple has to match with the entry that maintains the properties of the connection. That's the same entry as I described on the previous slide. However, now it has a different type, which signals that we also maintain information about the connection, how it looked before we translated it. I've mentioned several times already that the Linux contract is irrelevant, but it's not always the case. Sometimes it is good to use what Linux can do. And Linux can easily do SNAP. It is difficult to do that in eBPF. The problem is that it's difficult to allocate non-conflicting source ports. So if we need to do SNAT, for instance, a masquerade where we have net outgoing connections, that means connections that leave the cluster, but we need to send them with an external IP. We mark those connections and let them through the host network stack, we let them through IP tables, and let Linux do its job. Nevertheless, even in such a case, there must be a contract entry in the eBPF contract tables. You will just see something with a flag that says, okay, go through the IP tables. So far, we were talking about the networking part. But if you're using Calico, what you're probably most interested in are policies. So Calico takes the policies defined by the user and marries that with the information from the Kubernetes environment and has to program the data plane. Unlike in IP tables, where it programs the rules in a single point in the IP tables, in the eBPF case, it compiles the policies into a program which are attached to each endpoint. So the policy is scattered around many more places. It is difficult to verify that the policy is actually what you were hoping for, or at least until recently, that was a problem. Because the program is a binary blob that may refer to some eBPF maps, but to read it, you can perhaps disassemble it, but it's difficult to read it, and you would need to have intimate knowledge of the system, where to get those programs, and the data structures which are allowed and referred by those programs. So we have heard that complaint from some users in the past, and it also makes debugging for ourselves a bit tricky. So the last release includes what we call policy dump. With the Calico BPF, you can use the policy dump command to dump policies attached to a particular interface or an endpoint at a particular hook. The hook can be ingress or egress, and for host endpoints, it can be also XDP. This slide shows you a snippet of how the dump looks like. So it will tell you which policy is being implemented, tells you which rule is being implemented. It also gives you a little bit more human readable explanation of what the code actually does. And then it also gives you the actual annotated eBPF code. So you can, if you're really brave, go verify whether the code is correct and follow how the pieces of code interact with each other. I mentioned before that the policy can also refer to some BPF maps. We mostly use the BPF maps for IP sets. We borrow the term from IP tables because in the end of the day, it is really just a set of IPs. And these set of IPs are typically created when a policy uses a selector. And the selector collects a bunch of endpoints, a bunch of IPs that we have to match against. So the policy dump would also tell you which of the selectors created what sort of IP set, and then you can use the eBPF, the Calico BPF IP set dump to actually look at the individual IP sets, whether they match what you were expecting. With IP tables, one bit of information you can usually get is how many packets hit a certain rule, which gives you kind of an indication of whether packets were dropped and where they were dropped. So Calico eBPF now also comes with packet counter dumps. It gives you the usual how many packets were accepted, how many packets were dropped by policy, but it also tells you if packets are being dropped because of some errors and some problems. Those counters should be 0, right? So if they are not 0, it probably gives you some indication of what might be the problem of your network. One of the most important counters, though, are the counters that are included with the policy dumps. Every rule also includes a counter which is incremented every time a packet hits that rule. Note that we usually, not every packet of a connection hits the policy, right? When a connection is started, the first packet will hit the policy. If we allow that, we create a contract, and subsequent packets are let through if they are part of a known connection or a vetted connection. So don't expect to see counters incrementing with every single packet. But if you are troubleshooting whether the policies work the way you expect them to work, and you don't see counters being increased when you create new connections in the part of the policy that you would expect, then probably your policy is not doing exactly what you were hoping. Sometimes it can happen that none of what I've talked about before will help you to troubleshoot your issue. The ultimate option here is login. We can turn on login of the eBPF programs, which gives you traces of how the packet go through those programs. These logs are essentially print case from kernel, and they are directed into the trace pipe, and you can go and see them in various ways, one of which is the command up on the slide, and gives you extremely fine-grained insight into what is happening. However, it is mostly a fire hose, and all the packets are being logged and all the traces are being logged on all devices on the node, which obviously is a problem if you have a larger setup, if you have a setup which is busy, if it's typically in production. That is slow. It has an impact on performance, and also for troubleshooting, this is super hard to unpack. So what we are implementing and will be part of the upcoming release is much more fine-grained login. What we essentially do is we can use PCAP or TCP dump-like expressions to create filters that select which packets should be logged and which traces should be logged. What we pretty much do is we create a filter, we attach it before our TCP programs, and the filter decides whether it should go through the fast path without the overhead of login, or through the slow path that emits the logs. So this is ready to be used in production environments where vast majority of the traffic should go through completely unaffected. Only your troubleshooting traffic or troublesome traffic will take the hit and go through slow paths, but will also shed some light on what's happening. Why we use the PCAP filters? Well, it is a pretty well-known syntax which everybody who's using TCP dump understands. And the PCAP can also generate the BPF code. It is the classic BPF, which needs to be translated to eBPF. That's actually what also happens when you use TCP dump. It injects the classic BPF into the kernel, and the kernel translates it into eBPF. Note that we only prevent those filters when we actually turn on debugging. So if there is no debugging, there is no performance hit, there is no filter. And also know that both paths execute the very same policy. So logging doesn't create a security hole. And also, if you look at how you would achieve that in the IP tables with tracing in IP tables, this is much easier and much more intuitive to use. So stay tuned for the next release. I mentioned that the logging can be pretty fine-grained, and we can make it even finer by setting those expressions per device. So we don't have a single expression which is set globally, but a new option allows you to set whether you want to have it on all devices, whether you want to have it on a specific device, whether you want it for host endpoints or workload endpoints, and whether you want to set it per certain node or globally. So we hope that this will really speed up troubleshooting and will really make troubleshooting a pleasant experience. So let me walk you through an example of logging, since I was talking about it till now. What you would typically see is something that on the left-hand side has annotation of what interface the log comes from, and it also indicates whether it's been on ingress, egress, there will be an E, and or XDP, which we denote with X. On the right-hand side, you have the trace. Typically, for a single packet going through a single program, first you see some initial parsing where we have to figure out what sort of packet it is. In the next step, we have to do contract matching. In this case, there was no contract hit. That's unknown connection. It's a new connection. So we also try to match it with a service in a network address translation. there is no hit there either, that means this is a plain connection without any service. The next thing, we have to go through a policy. In this case, for simplicity, this is a host point with no policy, and we simply accept the packet. We create the contract, and then we decide where and how to forward the packet. In the more complex case, with the netting, what you would see is lines like I depict on this slide. First, the lookup would have a hit, and it would indicate what sort of service it hit and which backend it selected. And you can directly match it with the Calico not dump output. Later on, you would see that we've actually created a netting contract. So we've created the extra entry that I've been talking about before. And somewhere later on, you would also see the program is actually modifying the packet, which is patching in the new destination IP and the new destination port. And you get a sense of the full information. So let me wrap up here. I would like to conclude with the fact that eBPF is a really great tool. It is super flexible and super powerful, and it allows us to provide stuff that was not previously possible with IP tables. But it's also very important to understand that the eBPF data plane disrupts how the packets flow through the system. This is not bad. In many ways, it is good because it makes things faster. However, it may be confusing, and we need to provide new tools, and we need to provide more education. We're working on it, so don't be afraid. Go ahead and try our eBPF data plane. It's really great. Thank you for your attention.
Cloud-native applications can't be secured with the traditional security tools. You need a more active and granular level of security. Calico Cloud is an active cloud-native application protection platform that detects, prevents, and mitigates breaches in cloud-native applications. Let's look at how to secure your cloud-native environment at build time with Calico's container security. At build time, we want to make sure that images that the development team provides are clean and without major vulnerabilities or misconfigurations. All image registries are auto-populated and continuously scanned by Calico's scanning engine. I can also manually add new registries. It's very easy for me to see the results of the last scan from the Scan Results page. Pass-Fail is color-coded with specific scores. Details about each vulnerability that impacts each image are available on the right side. I can control which images can be displayed to my environment using admission control policies. I am only allowing images with pass or worn scan results. I've also enforced an upper limit for the age of a scan result. Now, if any application developer attempts to deploy an image that doesn't pass the security criteria, it will automatically be blocked. Once you have the admission policies in place, you may come across a situation where the application developer is telling you that a particular vulnerability does not impact their code and the way in which they are using the affected library. In this case, you need to create an exception. Calico Cloud offers a number of options to scope the exception to a specific image version, any version of this image, or any image. In addition to scanning and assessment of images, I must ensure the Kubernetes environment is also secure and does not have any misconfigurations. Calico helps you continuously assess your Kubernetes configuration using compliance reports that assess your configuration against CIS benchmarks. I scheduled my CIS benchmark report to run every 24 hours. The number of nodes passing or failing the CIS benchmark tests is color-coded. And here are the top failed tests. I can also download the full report to get more insight on each test and how to mitigate its risk. At this stage, I have scanned all my images, allowed the deployment of only those that pass the security requirements, and I have also assessed my deployment environment against CIS benchmarks. Try it yourself by signing up at www.calicocloud.io. Cloud-native applications can't be secured with the traditional security tools. You need a more active and granular level of security. Calico Cloud is an active cloud-native application protection platform that detects, prevents, and mitigates breaches in cloud-native applications. Let's look at how to secure your cloud-native environment at build time with Calico's container security. At build time, we want to make sure that images that the development team provides are clean and without major vulnerabilities or misconfigurations. All image registries are auto-populated and continuously scanned by Calico's scanning engine. I can also manually add new registries. It's very easy for me to see the results of the last scan from the scan results page. Pass-fail is color-coded with specific scores. Details about each vulnerability that impacts each image are available on the right side. I can control which images can be displayed to my environment using admission control policies. I am only allowing images with pass or worn scan results. I've also enforced an upper limit for the age of a scan result. Now, if any application developer attempts to deploy an image that doesn't pass the security criteria, it will automatically be blocked. Once you have the admission policies in place, you may come across a situation where the application developer is telling you that a particular vulnerability does not impact their code and the way in which they are using the affected library. In this case, you need to create an exception. Calico Cloud offers a number of options to scope the exception to a specific image version, any version of this image, or any image. In addition to scanning and assessment of images, I must ensure the Kubernetes environment is also secure and does not have any misconfigurations. Calico helps you continuously assess your Kubernetes configuration using compliance reports that assess your configuration against CIS benchmarks. I scheduled my CIS benchmark report to run every 24 hours. The number of nodes passing or failing the CIS benchmark tests is color-coded. And here are the top failed tests. I can also download the full report to get more insight on each test and how to mitigate its risk. At this stage, I have scanned all my images, allowed the deployment of only those that pass the security requirements, and I have also assessed my deployment environment against CIS benchmarks. Try it yourself by signing up at www.calicocloud.io.